Okay, so we're going to talk about different types of discontinuity. The first one is point. All right, so if you've got a graph, we had piecewise functions where we did this. A graph that might look something like a solid here, and then it jumps up and goes in another direction. It's considered a function because it passes the vertical line test, but it's discontinuous at a certain point, at whatever that point is. Actually, that's not point. Hold on. Point, sorry, that's jump. Point is something that looks like this. It's continuous except everywhere except for at one small place, one value. Okay. Hey, Emily, let's take notes. Okay. All right, infinite. The graphs never come together. It's what an infinite discontinuity looks like. So, for example, something that looks like this. These are going to be discontinuous infinitely. The graphs, the tails will never come together. Jump is what I first started to do, where it's continuous everywhere at a certain place. It pops up, it goes to another y value. So discontinuous means it's not a smooth graph. Not a smooth graph. All right, so if we're trying to figure out if a graph or a function is continuous, we've got three conditions that it has to follow. The first thing, the function exists at the point of interest. So whatever point we're looking at, whatever value of x we're looking at, we have to be able to use that value. So I said think about denominators. So for example, if I am giving you this as my function, and I want you to look at the value when x is 0, it would be undefined value, wouldn't it? So we would say it's discontinuous at that point. So if any one of these three reasons or these three cases that we try fails, the whole graph is discontinuous. If I did this one, well, go on. So we have to be able to, at the point of interest, we have to be able to use that value. The value of x, whatever value of x that we're looking at. And see if it's discontinuous. They're undefined or something. Okay. The function approaches the same y value from the left or the right of x. So, for example, if I gave you y equals 2x squared plus 3, and that's my function, and I want to look at what happens when x is equal to 1. So I'm just kind of showing you individual cases. So in this case, what we want to look at is we want to make a little chart. And these are going to be our x values. And we're going to look a little bit to the left and a little bit to the right of 1. And we don't want to look too far left and right. So, for example, I don't want to look at 0 and 2 because that's too far removed from our point of interest. So a little bit to the left might be 0.999. It's just a small smidge to the left. And another value is 0.99. We're getting further and further away from 1 on the left side of that value. This is what limits are. Okay? We looked a little bit to the right of 1. 1.001 or 1.01. And the values that we get, our y values, should be very close to the value when x is 1. Well, when x is 1, y is 5, because all we're going to do is plug it in. And we know that 1 is a usable value for x because it's not undefined. So would you agree that our value is very close to 5? At 0.99, what do we get? Yep. Again, really close to 5. Now, what is the shape of this? 2x squared plus 3. What is that a shape of? It's a parabola. So it's a parabola that's been shifted up 3 units. And we know that when x is 2, y is 5. And doesn't it make sense that we're getting really close to 5 from the left, and we're pretty close to 5 on the right side of that value? Does that make sense? On the left, we're going to be a little under 5, and on the right side, we're going to be a little bit over 5. Okay? So at 1.001, what value do we get? And then at 1.01, what do we get? And so you can see that I'm approaching 5 from both sides. It'll be really obvious. You might get 5 on one side and 6 on the other. So it won't make sense. So this is an example of when it does work. Okay? An example of when it wouldn't work would be if I gave you the functions 2x and x plus 3, and here when x is less than 3, and here when x is greater than, ooh, that works. We'll make this 4. Greater than or equal to 3. We know we can use 3, correct? Because 3 doesn't give us an undefined value either here or here. Does that make sense? So our next step is to see what do we get a little bit to the left? Well, over here, when we plug it in, what do we get? When x is 3, what do we get in this case? And if x is 6 for this one, what do we get? And then x is 3, what is y? 7. So is there any way that we're going to be approaching the same values from either point of that value of x? One will be becoming 6, and one will be approaching 7. Do you understand that? So this would be an example of where that doesn't work. That's a jumping line. All right. Y, the value that the function approaches from each side is the value you're supposed to get. In other words, and that's another example of this jumping one. All right. Can you use the value? Is it approaching the same value from the left and the right? And then, in a case like this, if I give you 3x minus 2 and x, and I'm looking at x is less than 2, or x is greater than or equal to 2, I have to get the same y value. So you have to get the same y value in each piece. This is a piecewise function, right? Of the function. So here, if x is 2, y is 4. Right? 6 minus 2 is 4. And here, when x is 2, y is 2. Because we're just plugging it in. And we don't have the same values. These values are not the same. So this would not be a continuous function. Are we good? All right, so let's look. Here's an example. Determine if y equals 3x squared plus x minus 7 at x equals 1 is continuous at that value when x is equal to 1. All right, so case number 1. Can we use x equals 1? That's the first question. Does it create an undefined value anywhere? We don't have a denominator, so we're good. Yes, we can use it. Okay. We're going to look a little bit to the right. 2. using whatever values. So this is going to be 0.999, 0.99. This is 1.001 and 1.01. So when x is 1, we know by plugging it into here, we're going to get -3. So that means as I go from the left side and the right side of that x value, I should get something very, very close to -3. So what happens when we plug in 0.999? What do we get? 3.00. I think I have 007. And at 0.99, what do we get? -3 point what? 07. Are we all getting the same answer, or are you just letting Ellen do all the work? All right, how about 1.001? What do you get there? I think this one's -2.93. So can you see that we approach -3 from both ways? We're coming towards -3, either decreasing or increasing. Meg?
For the first question, can't we use x equal 1? Is it only going to be no
If it's undefined or something weird happens, yeah.
So if there are denominators, so if there aren't denominators, then
You should be able to use it. Yeah. Yeah, because the only time that we have a point of interest or a point of concern is a denominator, right? Square roots have to be positive. Okay, Julia? I'm plugging it in. 3 times 1 squared is 3, plus 1 is 4, 4 minus 7 is -3. So I'm substituting it into that value. And that's where I'm getting all of these ones too, because I'm plugging 0.999 and 0.99 in. All right, the third one is, do I get, really it's just saying, do I get a value for y? And this one, this last case, is really a concern when you have jump functions, when you have piecewise functions. You just want to make sure that you're getting the same value for y. Obviously, we're getting a value for y. What does when x is equal to 1? We know y is equal to -3. So as long as we're able to get a value, then we can say this function is continuous. And this is the shape of a what? A parabola. And a parabola is a smooth function. So in our mind, because we know what this looks like, we have an idea that it probably should work. All right. What about the next one? It has a denominator. And can I use that value? So it fails the first case, right? Because if I plug in x equals -2 in, I'm going to get 0 over 0, which is undefined. Because of the 0 in the denominator, not because of the 0 in the numerator. We don't care about the numerators, we're worried about denominators. And if one case fails, they all fail. So this is discontinuous. Does that make sense? All right, so we go on. I'm looking at, in this case, when x is equal to -2. So the first question is, can I use -2? That's usually going to be at this point right here where it splits. So can I use -2 up here? Can I use it in for x squared? Yes. Can I use -2 in for here? No. Because what happens? And 4 minus 4 is 0. And so it's going to fail this case. Because we're going to get 1 over 0, which is undefined. So it's got to pass both of those those individual sections. So it passed the first one, it failed the second one, so this is not going to be a continuous function. This is going to be a jump function that's going to give us two separate values for y. So this is not continuous. Okay? Okay, so here we go. X squared minus 3 is my function. Can I use x equals 3? Does it exist? I can use it. I don't have a denominator, so it's all good. What's my chart going to look like? What value am I going to use to the right of 3? Or to the left of 3? Well, look at your numbers. Don't your numbers on a number line get bigger to the right and smaller to the left? So 2.999 and 2.99. To the right is what? And then, yeah. Those are my x values. Now I got to come up with my y's. Okay. So these are my y's and these are my x's. So when x is 3, I know that I'm going to get 6. I'm plugging it into that formula or that equation, correct? All right, what happens when I plug in 3.001? What do I get? Okay, pretty close to 6, isn't it? What about when I plug in 3.01? I'm getting a little bit further away from 3. Okay, and if I'm a little bit further away on the other side of 3, so I'm using 2.999, 5.994, so this is going to be 5 point. So I'm approaching 6 from both. So this is working, right? I'm clearly coming up to 6. All right, so this was case 2, and it works. Case 3 is, do I get an actual value for y? So when x is 3, what did we get for y? 6. So this is a continuous function. That's all 3 of the cases. You've got to show me this. So when you're quiz, when you have this kind of a problem, you got to show me all of your cases, or show me the case that doesn't work. Okay? All right, so then we talk about day 2. Let's see. Is there any more? Is it on the same? Okay. Here we go. We'll skip the warm-ups. When we talk about end behaviors of polynomials. Now, we did this last year. We did this, yes, last year. And if you were in my class, we body graphed. Okay? Positive functions that are even. So if the exponent is squared, highest exponent, or to the 4th, or to the 6th, and it's even, or it's positive, so the coefficient is positive, your tails are here and here. Right? Like a parabola. Your tails are going up, or your tails go down. So these are where your tails will fall if your coefficient is negative. Do you remember doing this? This was chapter 5 last year. All right. So this is positive infinity on the x-axis. This is negative infinity. This is positive infinity on the y. This is negative infinity. Do you remember doing this now? As x goes to positive infinity, what does f of x approach? That's the y. As I go right, am I going to go up or down to get to my tail? Oh, and up implies which kind of infinity? Positive infinity. As x approaches negative infinity, so as I go left on the graph, where is my tail, up or down? So f of x approaches positive infinity again. Remember doing this? I'm sorry? Yeah, if x goes to positive infinity, my function goes to positive. If x approaches negative infinity, my function goes to still positive because my tails are always up. Does this make sense? So here we have positive infinity, negative infinity, positive infinity, negative. So on this case, as x goes to positive infinity, what does my function go to? Down. And that means negative infinity, right? And as x goes to negative infinity, what is my function going to? Also negative infinity, because their tails are going down. Now this is just for the even functions, right? It's just the even functions whose coefficients are either positive or negative. So then we look at the odd functions. Well, remember, if the coefficient is positive, you're doing this. And if it's negative, you're doing this. Agreed? And so we put our infinity signs on here to help us. And we make the same statements again. If x is going to positive infinity, what is f of x approaching? Because it's going up, right? And if x goes to negative infinity, then my function goes to negative infinity. Because I'm going down. If I go left, I got to go down. If I go right, I got to go up. Okay, and if x goes to positive infinity, f of x goes to negative infinity. And as x goes to negative infinity, my function now goes to positive, right? If I go from here, if I go left, I got to go up to get to my tail. That's positive direction for the y values. Okay, then we talk about increasing, decreasing, and constant functions. This is what the book tells us. And it's pretty confusing. So I'm going to just show you what this is actually asking. Okay, let's go to the next one. We'll just kind of not worry about that. We'll come back to it. I just want you to know what this is. All right, graph the function and determine the intervals for which the function is increasing or decreasing. This is the shape of a what? Where is your vertex? 3. It shifts from here to 3 units to the right and not up or down, right? Okay. Is this a parabola that opens up or opens down? And we know that because negative. All right. Do you see how if you were to travel from on your graph from left to right, do you recognize that you are climbing a hill? And then at a certain point you are going down the hill. Would you agree? At what point, what x value do we change from going up the hill to down the hill? At what x value? All right. So what we need to know is that when x is less than 3, is our function increasing or decreasing? F of x is increasing. What's the second part of our function going to say then? As x is greater than 3, what is my function doing? Yes. Okay. I'm not going to do this one. I don't like that one. Let me just draw you something. Okay. Put a dot at 1, 2, 3, negative 3, 1, and let's see, I'm going to do this, and do this. For some reason every year this is difficult for you guys to see, and so I'm trying to give you more examples of this. Where is our graph turning? Because those are where we start our intervals. At what x values? At negative 3, it turns, right?
Oh, at X.
Right, it's only the x values. And then when x is 0, it turns, right? Do you agree? And it doesn't turn again. What is it doing over on this side? It's increasing. What's it doing here? Decreasing. What's it doing here? Increasing. Okay? So I need to say this mathematically. So what am I going to say for this first portion? When x is less than negative 3, f of x is what? Increasing. Okay, careful on this next one. When it's between what? 0 and negative 3, what is my function doing? It's decreasing. All right, so we've taken care of increasing, decreasing, and now we got to say one more thing about increasing. What's my last statement going to say? X is greater than 0. My function is, again, increasing. Now, the reason we're trying to identify this is we're going to look at it mathematically later on in this chapter. And we're going to verify. We're going to talk about zeros. We're going to do some synthetic division. You remember doing synthetic division? All right, all this is going to come into play in this chapter. Okay. Does this make sense? About how to figure out the intervals and when it increases and decreases, it really might be helpful for you to write increases. Oops, now it's decreasing. Oops, now it's increasing. If I'm writing these words 3 times, I need 3 intervals. If all I'm doing is saying increasing once and decreasing once, then I have 2 intervals that I have to indicate. Okay? Any questions on this?